Hi, this is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 1, Lecture 1, Essential Ideas. In this chapter, we will cover phase and classification of matters, physical and chemical properties, measurements, measurement uncertainty, accuracy and precision, and mathematical treatments of measures and results. These are the topics to be covered, but they may not be covered in this exact order. So let's get started. So what is chemistry? Chemistry is defined as the study of matter and the changes it undergoes. It is that straightforward of a definition. So chemistry looks at things around it and how does it undergo change and how does it interact as it undergoes that change. The processes involved in those changes and the events of those changes is what chemistry examines and what chemistry is all about. So, what's matter? Matter is anything that occupies space and has mass. Look around you now and you'll see lots of things that matter. You see lots of matter all around you. If it occupies space, if it has mass, which we occasionally confuse with weight, we'll define those later in this chapter about how to differentiate them. But if it has mass, then it is matter. Okay? A substance is a form of matter that has a definite composition and distinct properties. If it has a definite composition, has distinct properties, then it's matter. Table salt is matter. It's composed of sodium chloride, that is sodium and chloride, and therefore it is a substance. And there are many, many other substances. Your smoothie is a substance. Your hamburger from the restaurant is a substance. Mercury is a substance. Gold. These are all substances because they have definite composition and distinct properties. You would do well to memorize these definitions. The study of chemistry involves two broad areas or two major areas of concern. One is the micro scale, that is the very large scale. That involves the things you can see on a daily basis, things you interact with. Okay, the example shown in this particular slide shows rusting nails. These are things you can see, you can experience without any particular unique equipment, microscopes or what have you, any analytical instruments. You don't need any of those types of things. You can simply see these things and you can enjoy them, you can participate in them. That's the micro scale. It's the very large scale. For example, water is water. It's wet, you see it, you interact with it, you drink it, you bathe in it, you swim in it. That's the micro scale involvement of chemistry. And then there's the MIC micro scale. In the micro scale, this is the science and chemistry that's occurring below the scene, the things you can't see with the naked eye, the things you can't observe on a daily basis, but it is there. And it can be observed using special instrumentation. In the case of iron rusting, it is a reaction between iron, Fe, from the periodic table, which you will learn about, and oxygen, O2, which is a diatomic gas in its natural state, which you will learn about, to form iron 3 oxide, which you will learn how to name, and you will learn how to perform chemistry with these types of elements. This is a micro scale. And to represent this micro scale, chemists will use symbols that are written in our case, English, to represent them. So we have Fe, which is iron, and we have oxygen, which is O2. That is the symbol for oxygen. It is not oxygen, but it's the symbol for oxygen. Therefore, we call it oxygen. And we have Fe2O3, which is iron. We have two atoms, 2 units, 2 molecules of iron combined with 3 atoms, 3 molecules of oxygen to give us the the iron 3 oxide, which we refer to in everyday language as simply rust. So this is how rust is formed, and this is a type of chemistry that we will be studying, and you will understand how to do all of these things at the end of this course. Now, chemists like to use an organized fashion for examining chemistry and for understanding chemistry and the events of chemistry. That organized methodology is called the scientific method. So, what's the definition? The scientific method is a systematic approach to research. That's it. When scientists carry out research, it's carried out in a systematic fashion known as scientific method. And this process becomes, frankly, second nature to scientists and to chemists. Okay? There are three major events or unit operations that occurs in the scientific method. One is called the observation. This is where things are simply observed. Okay, that's it. You look at it, you see it, you notice something about it, and you make notes of that, or you record those observations. Is it purple? Is it blue? Is it hot? Is it cold? Is it large? Is it small? Does it swell? Does it shrink? You observe these things. And then you put them in some type of format, which the representation. How do you convey that information? How is that information dealt with? How do you handle that information? And we're going to show you some other things involved in what we call representation. But essentially in that part, it's really in a sense, how do we handle these observations, and what do we do with them to validate them or to determine how they can be further used in science. And then from that, we have to interpret it. What does it mean? And here's where scientists, the best scientists, tend to be somewhat robotic about that. In other words, the data are what the data are. What the data says is what the data says. That's it. And so what scientists would do then is interpret that based upon some reasonable principles. And those principles are scientific in its basis. Okay? So scientists will use scientific methods for interpreting the data. Okay? Now, that brings to a very important output from the data or from the observations or from, frankly, dealing with these three broad unit operations or these three broad areas of thought. A hypothesis is a tentative explanation for a set of observations. So this hypothesis is developed and it's tested over and over again, and it's modified as we go. Occasionally this hypothesis will drift into, frankly, the representation and interpretation areas. It cannot be avoided. But for the most part, the hypothesis will try to move itself back to what was observed when you think about how I'm starting to interpret, how I'm starting to put together a format by which to assess what's been observed. So you start to develop some hypothesis. Now, hypothesis will help drive the representation, which will help drive how it's interpreted. And that's tested, modified over and over again, with the goal being to come to some reasonable output that makes scientific sense and matches what science says should be possible. So, what does that engine look like that drives this scientific process? Or what does it look like to be involved in the scientific method? In the end, the scientific method has two broad conclusions it reaches. One area is called laws, okay? And we'll talk more about what it means to have a law. The other is it looks to reach some conclusions and some theory about what's happening, okay? These are the two logical outputs from the scientific process, law and conclusion. The law involves an output that has now become what we know to be true based on all the observations, and that what we know to be true does not change within reason. For example, gravity, it is a law, okay, that gravity pulls on objects. That is a law that is established. A mathematical law is 2 plus 2 equals 4. 2 plus 2 will always equal 4. Okay? So this is what a law is. It establishes a standard by which other observations may be judged, because these observations have proven themselves to be absolutely true. Another law is we need oxygen to breathe. These are all laws. Okay? And once these laws are established, we use them to help understand our other observations. Another law is that elements on the periodic table, which you will learn about, when they react in a certain well-defined fashion, a well-defined order, and sodium plus chloride gives us sodium chloride. That is a law that is acting, such that when sodium reacts with chloride, we will get this. The law is that these elements will react in a balanced equation. That is the law for reactions. Okay? Then we have conclusions and theories. Conclusions, what we reach after having gone through the experiment a few times. For example, if I bake my cake at 300 degrees C, I discover that it has a different texture than if I bake it at 250 degrees C. Okay? So the conclusion is I have to choose the best temperature for baking my cake, or what have you. Okay? This is a conclusion that you reach from the experiment. Another example of an experiment might be, if I drive on this highway at high speed, I get traffic tickets. Okay? You've run the experiment enough times, you've done it enough, you get tickets, grandma gets tickets, everybody gets tickets when they drive that highway above the speeds, which, by the way, you should not be doing. But if you do it, the conclusion is that if I drive this highway, it's very likely that I will get a ticket, which is also a theory. When that theory comes to pass, you discover that you reach the conclusion, yes, this theory makes sense. Okay? So that's the law and the conclusion. The law, again, is a set of observations that have now been proven over and over again to be true. Observations and conclusions are often reached on shorter-term information that serves that immediate purpose that, as we continue, may become law. Okay? To get to these, scientists follow the scientific method involving 4 key steps, or 4 key events. And you do well to memorize these definitions. The first one is observations. Observations are facts obtained by observing and measuring events in nature. Then there's a hypothesis. A hypothesis is a statement that explains the observation. You notice something you observed, and you say, this could be occurring because the beeping of your smoke detector could be because the battery is low. Or it could be because the smoke detector is broken. These are hypotheses that you test. Add a new battery and it continues to beep. You say, perhaps the smoke detector is broken. I replaced the smoke detector and the battery, and I discover that, it works now. Because I've carried out the experiment. That is what the experiment is for. The experiment are procedures to test the hypothesis. So we carry out some steps to systematically test the hypothesis. For example, for the smoke detector, I wouldn't change the battery and the smoke detector at the same time because I've carried out 2 events, and therefore I might not know which event was really the problem. So I would systematically change, and in my case, I would change the battery first, and then perhaps the smoke detector. A theory is a model that describes how observations occur using experimental results. A model describes how the observations occur using experimental results. So you use the experimental results to actually bring life, if you will, to the observations. Okay? So this is a scientific method, and it is a methodology that is used in chemistry, and is a methodology that is expected that students of chemistry learn and understand the definitions of. So let's restate the definition of a law and theory in a more concise fashion. You ready? A law is a concise statement of a relationship between phenomena that is always the same under the same conditions. Okay? It always happens that way. For example, force equals mass times acceleration. That's the law. It does not change. A theory is a unifying principle that explains a body of facts and or those laws that are based on them. For example, the atomic theory of chemistry. The atomic theory helps us to understand how atoms, how elements combine to give new materials, new substances, new forms of matter. Okay, and there are theories associated with that. If I combine these elements, it is likely I will get this substance. Theory supports that. We take those theories, we experiment with them, we carry them through the scientific process, and we get an output. From the output, we reach a conclusion and perhaps a new theory, or it substantiates the law. So how do we identify matter? Well, matter is anything that occupies space and has mass. So, if it occupies space and it has mass, it matters. Mass measures the quantity of matter. How much matter do I have? That's called mass. And the SI units, which you'll learn as we go through the course, the SI unit, which involves the International System for measurements, which is quite similar to the metric system, and in fact, it advanced the metric system to what we have today, as again the SI measurement process, which you will learn. So the SI unit of mass is kilogram. Okay, and we know that 1 kilogram is 1,000 grams, which is 1 times 10 to the 3 gram. And that's important to note. You will find conversion factors in this course. More times than not, those conversion factors, other than an example of this, knowing that 1 kilo equals 1,000 grams, oftentimes those conversion factors will be given to you. Okay? So mass is how we measure the quantity of matter. We want to know what the quantity of matter is, we measure it. Mass is independent of gravity. That is how we differentiate mass from weight. Weight, okay, has the force of matter, has a force of gravity exerted on it. So weight involves the mass that has gravity pulling on the object. Okay? So since weight depends on gravity, it will change from location to location. Mass will not change from location to location. Higher altitude location will have lower weight for the same mass. This is why for determining mass, a balance and a scientific balance is used. For determining weight, a weighing scale is used because the electronic balance is independent of the force of gravity. The scale at your home is not independent of the force of gravity. How do we classify matter? We classify matter in this course using 4 different forms: solids, liquids, gases, and plasma. Most people are familiar with solids, liquids, and gases. Plasma is an area that is not as obvious and not as readily available or observable to most people. Although it does occur each time lightning strikes, we get a plasma. Okay. So solid, liquids, and gases you're most familiar with. Most people are. And then we have plasma. So we'll be talking about these 4 areas of matter. When we look at matter, it is composed of, it may be subdivided into 2 categories: pure substances and mixtures. A mixture can be physically separated back into pure substances. For example, you may have a mixture of air, which is oxygen and nitrogen, almost 80%, about 78-79% nitrogen, and slightly under 20% oxygen, about 1% of other materials. This can be separated, not in a normal household, but in a laboratory it can be separated. So as long as it can be separated, it's a mixture back into pure substances. You'll know there's a pure substance if you look at the periodic table and you see the materials on the periodic table. It's a pure substance. If you see iron on the periodic table, it's a pure substance. If you see iron 3 oxide it comes from materials on the periodic table. It is a pure substance. That is the fastest way to identify pure substance. Simply look at the periodic table. Is it an element or a combination of elements from the periodic table? If the answer is yes, then it's pure substance. That's why we subdivide pure substance into elements and compounds. Compounds are formed from elements. Therefore, to separate compounds, we have to use chemical separation methods to go in that direction. So to move from compounds back to elements, we use a chemical process to carry that out. Okay? So those are pure substances. And then we have the mixtures. Mixtures are subdivided into heterogeneous and homogeneous. Okay? Now, you should also note, back to the pure substances, elements are further actually, or the smaller component of elements are atoms, which you will also learn about. Those atoms will be in the forms of ions that you will also learn about. So on the side of this table where we see elements, note that elements are formed from subatomic particles known as atoms. Those subatomic particles are further subdivided into protons, neutrons, and electrons, which you will learn about. But you do well now to note that when you in any discussion about atoms, protons, neutrons, and electrons, that is under the area of elements in this particular diagram. So, and we also have ions that will come together to form compounds, all on the side of pure substances. Okay? So, we have matter, and matter can be divided into pure substances and mixtures. Pure substances may be elements or compounds based on the periodic table. Mixtures may be heterogeneous with a composition that varies throughout, such as gravel, chocolate chip cookies, pulp lemonade or pulp orange juice, or homogeneous, which is a uniform composition throughout. So a homogeneous would be making Kool-Aid, would be making any mixture that you cannot easily differentiate. It would be making chicken broth. But oftentimes, chicken broth may not be a good example because the oils will allow it to separate. So let's leave chicken broth out of our discussion of homogeneous because it's not a real good example. A smoothie is an example, by the way, of a heterogeneous composition. Butter is an example of a homogeneous. Homogenized milk, which is the case for most milk today, is an example of homogeneous throughout. You do well to Google a few homogeneous and heterogeneous to help further understand this concept. So let's recap. We have pure substances, to which elements and compounds belong. We have mixtures where they're heterogeneous and homogeneous. These come together to make up matter as well as the subatomic particles, atoms, which are composed of protons, neutrons, and electrons on the elements, and as well as ions that lead to certain compounds. And we observe these as solids, liquid gases, and plasma. So let's have a further discussion about three of these states of matter that we are most familiar with. The first one is solids. Solids are compact. Okay? A state of matter that has both definite shape and volume is called a solid. That's how we define a solid. In other words, it's compact. The atom molecules are really packed together. Okay? And that makes it more dense. Right? And we refer to that as a solid. It has a definite shape. Liquid is less compact than a solid. The atoms, the molecules, are spaced out a bit more. A state of matter that has a definite volume but no definite shape is called a liquid. It occupies or attains the shape of the container in which it is kept. In other words, if you pour it in a glass, it's shaped like the glass. You pour it in a jug, it's shaped like the jug. Whatever the shape of that container is, that's what the liquid will acquire. And again, it is less compact than a solid. The atoms there and the molecules are moving around more than they're moving in the solid. They're all vibrating, but liquids are not only vibrating, but they're separating further apart from each other. And then we have the least compact is gas, okay, of these three states of matter. So a liquid is a state of matter that has no definite shape as well as no definite volume. It's called the gas. It occupies all the space the container has. So it'll fill up a room. You put a gas in a room, it fills up the room. That's why if someone gas in the elevator, yeah, it will fill the entire elevator. Just don't be on there with them. So that's what a gas does. It fills the entire room. Okay? That's why gas on one side of the room, you can smell it on the other, or it interacts in the other room really fast, because these molecules are least compact. They're not highly interactive, and they disperse to fill whatever area it is involved with. Plasma is the fourth state of matter. A gaseous state of matter that contains an appreciable amount of electrical charged particles is a plasma. Essentially, that's what happens again with lightning. That's perhaps our best example. Plasma has unique properties distinct from ordinary gases, and that's what differentiates it as another state of matter. Plasma is found in certain high temperature environments. Naturally, it occurs in stars and lightning, and then man-made in television screens. They're in the plasma TV. Get it? So these are highly electrically charged particles that are different from different other gases. So it classifies as a fourth state of matter. Let's talk a little bit more about pure substance. Pure substances are identified as elements and compounds. An element is a substance that cannot be separated into simpler substances by chemical means. Okay? In other words, once you are at the elemental state, that is the lowest form of separation that's possible for it. In other words, you can't separate carbon into something else. It's carbon. That's it. Okay? You can't separate iron into something else. It's iron. And so on and so forth. A compound is a substance composed of atoms or elements of two or more elements chemically uniting in a fixed proportion. In other words, there is a defined ratio for carbon dioxide, CO2, which is the gas, the smog or the smoke you see at the concerts more times than not. It's CO2. Okay? Compounds can only be separated into pure compounds, elements, by chemical means. So if you have a compound, you need chemical means to separate it. It can't be done physically. Pure substances may be elements or compounds. That is a take-home key point that you do well to retain. Pure substances may be elements or compounds. And if you take a look at the periodic table, you'll be able to identify pure elements right away. If it's on the periodic table, it's a pure substance. A mixture, however, is a combination of two or more substances in which the substances retain their distinct identities. They're distinct, they're mixed together, but they still have their identity. A homogeneous mixture is composed of a mixture it's the same throughout. If you scoop from one side of the area and you scoop from another side of the area, it will be exactly the same. Okay? A heterogeneous mixture, on the other hand, is composed of substances that are not uniform throughout. You get a different proportion when you eat it. For example, a granola bar is a heterogeneous, and so is a chocolate chip cookie, because you get a different distribution of the materials depending on where you bite the cookie or the granola bar. It can be separated by physical means. It may not be easy, but it is possible to simply pick out all the chocolate chips again from the chocolate chip cookie. Okay? It is not possible to pick out the components of milk from homogenized milk. And at one point, milk was not homogenized, and therefore you had to shake the milk. Now milk is homogenized, and because it's homogenized, it is now homogeneous. Okay? And cannot be easily separated. Physical means can be used to separate a mixture into pure components. Here's some examples to further clarify what we're talking about. Potato paste is a mixture. Aluminum foil, pure substance, because aluminum is on the periodic table. Helium, which is used in the helium-filled balloons for birthday parties, is a pure substance. And air is a mixture of nitrogen, oxygen, and a few minor components, with nitrogen being the major. Nitrogen is there to dilute the oxygen so that we can breathe it. And then there's 1% of other materials, and that includes also impurities as well. Examples of homogeneous and heterogeneous. Hot fudge sundae is a heterogeneous. Baby shampoo is homogeneous. Sugar water is homogeneous, but a peach pie is heterogeneous, or cherry pie, whatever your favorite pie is. Now, when we think about matter, there are certain laws that we use to help guide our thinking about how to interact with that matter, or actually how the matter interacts with us and interacts with its environment. One of those laws is called the law of conservation of matter. What is that law? It means that there is no detectable change in the total quantity of matter present when matter is converted from one type to another. Put simply, you cannot destroy or create matter. Okay? That is what this law means. Again, you cannot create or destroy matter. It may be transformed into another substance, but the mass balance will be the same as the original mass. This principle, this law, it's a law, by the way, this law is true for both chemical and physical change. If you tear paper, you still have the same mass. Okay? If you bake cookies, you have the same mass. The gases have come out, and they're in the oven, and they float around the house, but they're still there. If you could collect them all, you discover you have the same mass. And that is what the law of conservation of matter. Can't create nor destroy matter. Okay? There is no detectable difference between what you start with and what you end up when you transform a substance. That is the law of conservation of matter. And whether it's a physical change or a chemical change, the law holds. Now, we noted that you cannot create nor destroy matter, and that the holds for a physical or chemical property. So what is a physical and chemical property? Let's talk about it. A physical or chemical property involves the characteristics that enables us to distinguish one substance from another. These are what the properties are. And those properties are either in a chemical or physical fashion. Okay? So that's what properties are. They allow us to distinguish one substance from another. And it occurs either by a physical property or by a chemical property. A physical property is a characteristic of matter that is not associated with a change in its chemical composition. In other words, you just change the shape or the size or something of that nature, but chemistry is exactly the same. Okay? Examples of physical property involves density, color, color in your hair, that's a physical property, hardness, melting, boiling point, and electrical conductivity. One way to think about physical property is to use the term "it is what it is." Okay? So if it is what it is, and that's just the nature of what it is, that's very likely a physical property. Okay? It's like that. Water is always wet. That's it. It is what it is. This is the density of water. It is what it is. You get it? That's the color of the wall. It is what it is. You get it? So it's the characteristic of matter that does not involve the change or manipulation of the chemical composition is a physical property. Okay? The change of one type of matter into another type, okay, or the inability to change is a chemical property. Okay? So some reactions won't occur because of their chemical properties. Other reactions will occur because of their chemical properties. So the term react is a giveaway in any problem that is going to be a chemical property. If it involves a reactive change, then that's going to be a chemical property. Examples: flammability, toxicity, acidity, reactivity, and heat of combustion. These are all related to some form of chemistry that occurs. Flammability, the term you'll hear, is combustion or burning. So if it burns, combusts, or flames, it is a chemical property. Toxicity is toxic because of some type of reaction. Acidity, it involves some type of chemical interaction. Okay? And obviously reactivity does. And then heat of combustion. Heat of combustion. Combustion tells you that it is an indicator, at least, that it is a chemical process. All right? So a physical change does not alter the composition or identity of the substance. You'll want to know that. Ice melting. Ice melting is still water. Water evaporating is still physical. Okay? Sugar dissolving in water is still sugar in water. If you had tweezers small enough, you could pull the sugar right back out. A chemical change alters the composition or identity of the substance involved. Hydrogen burns in air to form water. That's what happens. When it burns, it combusts, flames. We know that that is a chemical process. Now let's take a look at some tables that summarize physical and chemical properties. So here are some examples. Physical change. Water boils to form water vapor. That is a physical change because it simply goes from one state to another. It goes from a liquid state to a vapor or gas state. Phase changes are physical changes. Copper is drawn into thin copper wires. When we draw copper into thin copper wires, we simply change the shape. If the only thing that happens is a change in the shape, then that is a physical change. It's like tearing the newspaper, breaking a pencil, breaking a branch off of a tree. That is a physical change. Sugar dissolves in water to form a solution. That is a physical change. You still have sugar, but it's dissolved in the water. So what you have is sugar surrounded by water, but it's still sugar. Paper is cut into tiny pieces of confetti, or you put it into a paper shredder. It's still paper, it's just chopped up paper. So those examples of physical changes. Now, let's contrast that with chemical changes. You have shiny silver metal reacts in air to form a black, grainy coating. That is a chemical change because it went from the shiny material to a black material. It has a grainy coating. All of these are indicators of chemistry taking place on the surface of this metal. Therefore, it is a chemical change. A piece of wood burns with a bright flame and produces heat, ash, carbon dioxide, and water vapor. That's combustion. Anytime it's burning, that's a chemical change. Okay? It is combustion. Burning, flame, those are giveaways that it's going to be a chemical reaction, a chemical change. Heating white granular sugar forms a smooth caramel colored substance. That is a chemical change. You're caramelizing the sugar. That's what you do when you bake things. Iron, which is gray and shiny, combines with oxygen to form orange-red rust. That is a chemical change because a chemical reaction occurs. There's a change in the chemical composition of the material. And that's how we differentiate a chemical change from a physical change. Let's take a look at this table, a summary of physical and chemical properties and changes. So let's take a look at a physical property. Here's the example. A characteristic of a substance: color, shape, odor, luster, size, melting point, or density. These are all physical properties. So if we talk about any of these types of properties, it's called a physical property. Okay? And we've already taken a look at the physical changes. So let's summarize them. A change in physical property that retains the identity of the substance. A change in the state, a change in the size, or a change in shape. These will be all physical changes. Contrast that with a chemical property, a characteristic that indicates the ability of a substance to form another substance. Paper can burn, iron can rust, silver can tarnish. We looked at the examples. This summarizes what we now know about a chemical property. There is a reaction that occurs. It changes the fundamental composition of the material. A chemical change, a change in which the original substance is converted to one or more new substances. Again, paper burns, iron rusts, silver tarnishes. These are all examples of chemical changes. So to reinforce this a bit further, let's use these examples. Classify each of the following properties as either physical or chemical. I've already worked through them for you. So ice melts in the sun, physical. Copper is a shiny metal, physical. Paper can burn, chemical. A silver knife can tarnish, that's chemistry, that's a chemical change. A magnet removes iron particles, that is physical. It simply extracts them, picks them up, lifts them out, captures them. That's just physical. Okay? Classify each of the following changes as either physical or chemical. Burning a candle, ice melting on the street, toasting a marshmallow, cutting a pizza, iron rust in an old car. What are they? Iron rust in an old car, chemical. Cutting a pizza, physical. Toasting a marshmallow, chemical. Ice melting on the street, physical. Burning a candle, chemical. So these are examples of physical and chemical properties and changes. When scientists think about properties of matter and how matter interacts and whether it's chemical or physical interactions, there are two important other properties that we use or that you must understand to be able to fully grasp this area of discussion. That is, we have to understand how to differentiate between extensive and intensive properties. Let me say that again. Extensive and intensive properties. Okay? And here's how we do it. An extensive property of material depends upon how much matter is being considered. So when we think about how much matter, we're thinking as an extensive property of matter. So that involves mass, how much, length, how long, volume, how much, you get it? So when we think like this of how much matter is involved, then that is called an extensive property. In other words, mass are different depending on the mass you choose or the substance you choose. Length is different depending on what you pick up. Volume is different depending on whether it's a swimming pool, a bathtub, or your drinking glass. Okay, so these things all matter. These are extensive. It depends on how much it does. Fuel in your tank. Okay, fill in the tank. That's an extensive property. Intensive properties of a material does not depend upon how much matter is being used. The density of water is the density of water. The temperature is the temperature. The color is the color. It is what it is. It doesn't matter how much you have. It's the same density. It doesn't matter whether you're on this side of the room or the other side of the room. Around the world, temperature is temperature. It's either 32 degrees or it's 50 degrees or it's whatever the temperature is. Color is color. It's red, it's yellow, it's blue, it's purple. You got it? These are intensive. So if it doesn't depend on any other factors, okay, such as the amount of matter, then it's intensive. If it depends on the amount of matter, then it's extensive. When scientists record or report their data, a system known as the International System of Units, the SI system, is used. Okay? Chemists use the metric system and the International System of Units, okay, for measurements when they measure quantities, do experiments, or solve problems. So it is the metric system, or actually an advancement of the metric system. The SI system uses the metric format for deciding how units will be reported as scientists. Okay, so it is the metric system, but it's been established as the standard form of the metric system, and again, it's called the SI system. Okay, all right. Your weight, for example, on bathroom scale, okay, is reported in pounds. In the SI system, it will be reported in kilograms. So let's talk about measurements. What are the measurements? And what is the definition of a measurement? Measurements involve the information that is basic, that is the basis for most of the hypotheses, theories, and laws in chemistry. Let me repeat that. Measurements provide the information that is the basis of most of the hypotheses, theories, and laws in chemistry. In other words, how do we measure this? And when we measure it and report it in the SI system. You get it? All right? Every measurement provides three kinds of information. The size or magnitude of the measurement, that's a number, some value, some digits. You got to have digits, okay? The second thing it provides is a standard of comparison of the measurement. What are the units? Inches, pounds, etc. And an indication of the uncertainty of the measurement. When we talk about the measurement, you have to have digits. So we report digits. And at the end of each of those digits, we report units. Those units are reported in the SI system for scientists. Okay? We don't report pounds, we report kilograms. We don't report inches, we report centimeters, millimeters, meters. Okay? An indication of uncertainty of accuracy is reported oftentimes for scientists, and you will learn this, we report in what we call significant figures. We also report, when we measure, a guess digit after each measurement. These are the standards of performance that you'll be learning in this course. What the digits are, the units for reporting these digits, and what is the uncertainty. So each time you report a number in this course, in Gen Chem, you want to think, what are the digits? What units are associated with those digits? And how do I report the accuracy, okay, or the uncertainty, of the measurement? That's important. And all three features is what chemists and what instructors of Gen Chem will look for in reporting of numbers, of values. They'll always look for the magnitude and the order of the numbers. They will look at the units, and they will look at the uncertainty in terms of how you might be evaluated. So again, the SI units is what we use. Without units, numbers can be meaningless or confusing. Therefore, we stick with the SI method of carrying out these operations. We want to make sure we reiterate that the SI unit of measurement is what is used for reporting numbers in science, and particularly in Gen Chem. Actually, in any chemistry, frankly. Okay? Here, this table shows you an example of the abbreviations of these. We won't spend time on these, but you do well to memorize them. There is an expectation that you will know these units. You'll know the metric, and you'll know the SI. And that is where the subtle differentiation occurs. The metric, the SI is based upon the metric, but it advanced the metric to a more systematic fashion that scientists use around the world. So it's not just metric, it is the SI use of the metric system for reporting science. For example, note how in the metric system you have liters, but in the SI system it's meters cubed. Note that in the metric you have grams and then you have kilograms. Okay? In the metric you have degrees C, and in the SI you have Kelvin. And Kelvin does not have a degree. It's not degrees Kelvin. It is simply Kelvin. And that's 273.15, I believe, is the proper digits added to the degrees C. So K equals C plus a factor of 273 and some decimals. Okay? It's important to differentiate this and note. Now, in most Gen Chem classes, professors will tend to accept liters and tend to be okay with that. So you're going to be aware of that and be aware of what's happening in your course. So liters are well accepted in most Gen Chem classes instead of meter cube. So be aware of that liters are accepted form in most Gen Chem classes. But you want to know the difference is that the SI unit actually takes the metric system a step further. Okay? Also note the second table on this slide shows you the units for some other things that you want to be familiar with. So you do well to know where this table is and be ready to use it. Let's talk a bit further about volume. Here in the SI system, volume, SI derived units for volume is cubic meter. So you have MQ, that is the unit. Be aware that if you cube a digit, if you cube a digit, you must cube the unit. So be aware of that. So here it shows you what happens in centimeter cube, decimeter cube, and it shows you conversion for liters. So these are conversions you want to be familiar with. Oftentimes, in many CHEM classes, many professors will give you the conversion factors, but when it involves units such as 10 to some power, there's an expectation that you'll know what kilo, okay, milli, okay, deci, these terms mean. So volume takes a 3-dimension, okay, essentially length, width, and height. Okay, it doesn't matter which way you take them, as long as it's 3 units, you get a cube. That is a volume, and we measure the volume in the laboratories in glassware. This shows you the SI unit for prefixes that you want to be aware of and what their meanings are. Fractional or multiple SI units are named using a prefix and the name of the base unit, and so you want to be aware of that. Okay, and the one on the left side of this slide, you see the ones that are very small. You know they're always small. When you see 10 to the minus, that's going to be a small digit. For digits that are large, they'll be to the positive, which we show you on the right side. You do well to take a look at these and be familiar with them. This table 1.3 prefixes used with the SI unit, repeats some of that, but gives it to you a little bit more detail. So you will want to review these slides and be familiar with how these units are used. Okay, so that completes Lecture 1 of Chapter 1. Stay tuned for Lecture 2 of Chapter 1.